Next up is the Semaphore API. So what is a semaphore? Semaphores are used for exception control in shared memory access and other features. For example, when accessing shared memory, an application can use an API to request a semaphore from the RTOS. If nothing else is accessing this shared memory, the RTOS gives a semaphore to the requesting task. The task can then access the shared memory, and when complete, it uses an API to get the RTOS to release the semaphore. When a task wants to acquire a semaphore, it invokes the Acquire Semaphore API, indicating the desired semaphore ID. And when it wants to release it, the task invokes the Release Semaphore API, again indicating the semaphore ID. Usually, semaphores are designated as counting semaphores. They offer resources for numbering and counting. Let's look at operations when an API connected to semaphores is invoked. In this example, the semaphore ID is 5 and the number of semaphores is 3. Let's start with the semaphores being unassigned to any task. A given task requests a semaphore using the Acquire Semaphore API. The RTOS assigns one of the 3 semaphores. Next, a different task also requests a semaphore through the Acquire Semaphore API, so the RTOS assigns another semaphore. When another request comes, the RTOS assigns a semaphore once again. So let's now assume that another separate task, task B, requests a semaphore. Since there are none available to assign, the RTOS will make task B wait. In other words, this task is moved to waiting state. For these situations, there is a semaphore wait queue, and task B is placed at the end of this queue to wait. If another task, task D, requests a semaphore, the RTOS will transfer it to waiting and place it in the semaphore queue, as with task B. Next, let's assume that a task holding a semaphore releases it through the Release Semaphore API. The RTOS will assign this semaphore to task B and move it from waiting to ready. When another task holding a semaphore releases it through the Release Semaphore API, again the RTOS will assign this semaphore to task D and move it from waiting to ready. At the same time, if a task holding a semaphore releases it through the Release Semaphore API, and there are no waiting tasks, the RTOS will manage the unassigned semaphore. Thus, as semaphores are released, the RTOS gets more to manage. So we can see that the RTOS doesn't just assign semaphores. It can help improve efficient CPU utilization by placing programs into waiting and delaying execution until they get a semaphore, thus giving execution rights to other tasks during that period. What's more, in terms of programming tasks, since the task only has to invoke the Acquire Semaphore API when it wants a semaphore, and the RTOS handles all processing from then until the semaphore is acquired, software architecture can be made simpler and software reliability improved. As we explained on the previous page, when a task invokes the Acquire Semaphore API, but no semaphores are available, the task is enqueued in the semaphore wait queue. So how does this semaphore wait queue work? There are semaphore wait queues like this for every semaphore ID. What's more, within each semaphore ID, there is a queue for each task priority level, the same as the ready queue. This means that tasks waiting for a semaphore line up in order of priority, and when they have the same level of priority, the task which was assigned to the wait queue first will get a semaphore first. The number of semaphore wait queues is the number of semaphore IDs times the number of priority levels. And so many queues are necessary. As explained earlier, semaphores are used in exception control. As this diagram shows, semaphores are assigned to each object like the shared table, shared I/O, and other resources needing exception control. Next, we'll look at the event flag and related APIs. The event flag is a system to raise a flag for signaling other tasks. It's used for intertask communication or intertask synchronization, so to speak. When a task invokes the wait flag API indicating an awaited event ID and flag pattern, the task goes into waiting until the indicated event ID flag pattern matches the indicated pattern. On the other hand, when the set flag API indicating an event ID and flag pattern is invoked, the indicated flag pattern will be written over the indicated event ID flag pattern. If there is a task waiting for this flag pattern, that task will move from waiting to ready. Let's use this diagram to look at operations when an API is invoked in a bit more detail. To begin with, Task 3 is awaiting an event, and Task 5 sets the event. In other words, we are showing that Task 3 wants to run a process, but before the next process can be run, Task 5 must finish. So Task 3 is waiting for this event. Task 3 invokes the wait flag API. The event ID used is 3. The awaited flag pattern is 0110. When an API is invoked, RTOS refers to event 3 in the event table. And since the pattern differs from the one indicated, it moves task 3 into waiting. At this time, just like with a semaphore, task 3 is enqueued into the event ID 3 wait queue. Now let's assume that task 5 uses the set flag API for event ID 3. This time, the flag pattern is 0100. This pattern is written to event 3 in the event table. This pattern doesn't meet task 3's wait release conditions, so task 3 is unaffected. If, however, task 5 uses the set flag API to set event ID 3 again, and this time the pattern is 0010, this flag pattern is written on top of the current event ID 3 pattern, making it 0110. Since this is the flag pattern task 3 was waiting for, task 3 is released from waiting and moved into ready state. It is moved from the event wait queue and enqueued in the ready queue. This is how the RTOS event flag function is used to make intertask synchronization and communication possible. Here you can see it written out on a timing chart. High priority task 1 invokes the wait flag API at this point. Task 1 moves into waiting. At this point, task 2 invokes the set flag API, and here, task 3 executes set flag. Since this fulfills task 1's wait release conditions, at this point, task 1 is released from waiting, and since task 1 is higher priority than task 3 is moved to ready state and task 1 into running. This chart offers an example application for the event flag. Separate data are being received on 2 communication ports, and processing starts on both at the same time. The receive task for communication port 1 is here. This is the communication port 2's receive task here. And here is the task for managing the data. The data management task waits for a flag with flag pattern 001, like this. When port 1 stops receiving, the receive task for port 1 sets the flag 0001. When port 2 stops receiving, the receive task for port 2 sets the flag 0010. When we program it like this, the data management task switches from waiting to ready when the data reception in both ports is completed. This is how event flags facilitate communication and synchronization between multiple tasks. Waiting tasks are enqueued in a wait queue, just like with semaphores. There are event flag wait queues for every event ID, just like with semaphores, and for each event ID there is a queue for every priority level. As a result, the number of queues is the number of event IDs times the number of priority levels. So again, just as with semaphores, it is necessary to implement multiple queues. Now we're going to show some other major APIs that RTOS can offer. The mailbox function allows the exchange of messages between tasks. Using the Send Message API, a message can be sent to the specified mailbox. Using the Receive Mailbox API, then, a task can retrieve messages from the specified mailbox. When used, if there are no messages in the mailbox, the task that invoked this API is moved to waiting and waits for a message to be sent to the mailbox. The fixed length and variable length memory pools are used to dynamically assign fixed or variable sized memory areas to each task. When the API requesting a memory area is invoked, if no memory is available, then the task is moved to waiting. These other APIs here are also used in many common embedded systems. Now we can talk about the features of APIs for moving into waiting. These are the APIs that cause the invoking task to move into waiting when invoked. They have the following features. Basically, these APIs cannot be invoked by the ISR or cyclic handler. This is because interrupts are disabled while handlers are executing, so they must terminate as quickly as possible. These APIs have a timeout option and a polling option. We'll discuss these next. First, we will explain the timeout option. The APs which can enter waiting shown here can indicate a timeout in their arguments. When they do so, even if their wait release condition is not fulfilled, after a set amount of time passes, the task moves from waiting to ready, and the software will be reactivated. As seen here, even if they are in the middle of the queue, if they time out, then they are retrieved from the wait queue and placed in the ready queue. With this feature, even if a software bug or other exception happens and prevents the wait condition from being fulfilled, you can prevent a lock from occurring. Next, we'll go into the polling option. There are situations where we want to use features from APIs which transition to waiting even from within the ISR or cyclic handler. In those situations, you can use the polling option. By doing so, you can get the results of the API without moving into waiting. For example, if you invoke the Acquire Semaphore API with the polling option, then depending on if a semaphore is available, it will return the value Semaphore Acquisition Success and acquire a semaphore, or Semaphore Acquisition Failure with no need to enter waiting state. This finishes our basic explanation of conventional software RTOS. Finally, I'd like to introduce Renesas Electronics' original technology, Hardware Real-Time OS. Renesas Hardware RTOS greatly minimizes overhead while improving API execution speed. For more details, please see our website.